GCE Advanced Level Chemistry Practical Series Experiment number 38. Experimental determination of the distribution coefficient of ethanoic acid between water and 1-butanol. The aim of this experiment is to examine the dissolution of a solute in two immiscible liquids. So students, now that we have understood the aim of this experiment, we can move on to identifying the equipment and the chemicals we will be using for this experiment. Students, now let's take a look at the chemicals and the equipment we will be using for this experiment. We'll be using sodium hydroxide. In this, we have sodium hydroxide solid, and using the sodium hydroxide solid, we have prepared a 0.5 moles per decimeters cube concentrated sodium hydroxide solution here. We have glacial acetic acid. Using this glacial acetic acid in this reagent bottle, we have prepared 2 moles per decimeters cube concentrated acetic acid solution, or in other words, ethanoic acid solution. And then we have butan-1-ol. We'll be using phenolphthalein in this experiment, measuring cylinders, distilled water, funnel, pipette fillers, graduated pipettes. Now we have 2 graduated pipettes here. You will be using 2 graduated pipettes in this experiment. Apart from that, we will be using these reagent bottles. We have labeled them as well because we will be needing 5 reagent bottles to hold 5 different mixtures that we will be preparing in this experiment. We will be using titration flasks. You will see at the end of this experiment, we will be carrying out a few titrations. So for that, we will be needing titration flasks. We have a separatory funnel. So we will be using this separatory funnel to separate the 2 immiscible layers of our mixture. You can see there is a ring holder here, or ring clamp, holding the separatory funnel, and we'll be using a burette along with a burette holder as well. Now students, we have identified the equipment and the chemicals we need for this experiment. Let's take a look at what we will be doing in this experiment. This experiment revolves around experimentally determining the distribution coefficient of ethanoic acid between water and 1-butanol. As you may already know, if you have 2 immiscible solvents in a mixture, and if you add a substance that can dissolve in both of these layers, at that point, the substance that you add will dissolve in each layer according to the solubility of the substance in each layer. In other words, when it comes to the experiment that we are carrying out, ethanoic acid is soluble in both water and 1-butanol. But there will be different solubilities of ethanoic acid in water and in 1-butanol. So when you have these 2 immiscible layers of water and 1-butanol, and when you add a little bit of ethanoic acid to these 2 layers, and if you mix the 2 layers, ethanoic acid will get distributed between these 2 layers and will develop a dynamic equilibrium. After a while, when the equilibrium has been obtained, the concentration of ethanoic acid in each layer will not change. So the distribution coefficient can be calculated taking these concentrations into consideration. So to calculate the concentration of ethanoic acid in each layer, we need to withdraw a small aliquot of each layer, and then we have to titrate it with 0.5 moles per decimeters cube concentrated sodium hydroxide to find out how many moles of ethanoic acid was found in each layer. After that, we can calculate the concentration of ethanoic acid in each layer. After calculating the concentration, we can proceed to calculating the distribution coefficient of ethanoic acid in butanol and water. So if you calculate Kd or distribution coefficient for one mixture, afterwards you can carry out the same few steps that we mentioned earlier and find out the distribution coefficient for other mixtures as well. At a given temperature, students, the distribution coefficient or Kd, or we call it the partition coefficient as well, this cannot change at a given temperature. No matter what other volume of acetic acid that we have added to these mixtures, the distribution coefficient will not change if the temperature is not changed. So therefore, although we may prepare a few different mixtures, when you calculate the distribution coefficient using each of the mixtures, you will see that the distribution coefficient is going to be more or less the same value, indicating that the given temperature distribution coefficient is a constant. So we are going to observe that reaction here today. After identifying the equipment and learning how we are going to be conducting this experiment, we can now move on to actually conducting this experiment. Now students, we are going to move on to the first step of this experiment. In the first step of our experiment, we need to measure 20 cubic centimeters, or in other words 20 milliliters of 1-butanol into each of these reagent bottles. After filling them with 20 milliliters of 1-butanol, we are going to then add different amounts of 2 moles per decimeters cube concentrated ethanoic acid solution. So we are going to add different amounts of 2 moles per decimeters cube concentrated ethanoic acid solution. For the reaction mixture 1, we will have 10 cubic centimeters of ethanoic acid, then 15, then 20, 25, and then 30 cubic centimeters of ethanoic acid. So you can see when we introduce different volumes of ethanoic acid into each of these reaction mixtures, we are essentially introducing different number of moles of ethanoic acid into each of these mixtures. Afterwards, we are going to be adding different volumes of water. We will add over here 25 milliliters of water, and then 20 milliliters of water, 15, 10, and 5 milliliters of water in that order. So reaction mixture 5 will have the highest number of moles of ethanoic acid, and reaction mixture 1 will have the lowest number of moles of ethanoic acid. However, in all of the mixtures, you will have both water and 1-butanol and a small amount of ethanoic acid as well. So keep in mind, students, the ethanoic acid solution is an aqueous solution. When we add ethanoic acid, we are essentially introducing a small amount of water along with it as well, because 2 moles per decimeters cube concentrated ethanoic acid is an aqueous solution. So we have different amounts of ethanoic acid added first, then later on we add different volumes of water as well. However, the volume of water in each of these reaction mixtures is going to remain a constant. In each of these mixtures, the volume of water is going to be 35 cubic centimeters, because for the reaction mixture 1, we will add 10 cubic centimeters of ethanoic acid, and we are going to add 25 cubic centimeters of water afterwards. So overall, the aqueous layer here is going to have a volume of 35 cubic centimeters. And then if you move on to the last one, over here in the reaction mixture 5 or mixture 5, we had 20 milliliters of butanol. To that we add 30 cubic centimeters of 2 moles per decimeter cube concentrated ethanoic acid. And finally, we are going to add 5 cubic centimeters of water. So 30 cubic centimeters of ethanoic acid solution is an aqueous layer, and 5 milliliters of water is also going to add to the same aqueous layer. So the aqueous layer is going to be 35 milliliters. So it is important to note that when it comes to each of these mixtures, we will have 20 milliliter layer of butan 1-ol and 35 cubic centimeter layer of aqueous medium. So, but the number of ethanoic acid in each of these reaction mixtures, number of moles of ethanoic acid in each of these mixtures is going to be different from one another. Again, when it comes to mixture number 1, you would only have 10 cubic centimeters of 2 moles per decimeter cube concentrated ethanoic acid, meaning it has a lower number of ethanoic acid moles. But as we move to the mixture 5, we can see gradually the volume of ethanoic acid we added increased, and over here in the mixture 5 we have 30 cubic centimeters of ethanoic acid. So therefore the highest number of moles of ethanoic acid is going to be present in this mixture. So after making note of that, now it is time for us to add 20 milliliters of butan 1-ol to each of these reagent bottles. So we have our reagent bottle number 1. We will add 20 cubic centimeters of butan 1-ol into each of these reagent bottles. In order to do that, we will take a small volume of butan 1-ol to this clean beaker here. After that, with the use of a measuring cylinder, we can measure 20 milliliters accurately. So we have a measuring cylinder here. Let's measure 20 milliliters using the measuring cylinder. We have measured exactly 20 milliliters. And now, after we measured 20 milliliters of butan 1-ol, we are going to transfer that into this reagent bottle over here. After transferring all of the butan 1-ol to the reagent bottle, we can stopper the reagent bottle and we can keep it aside, and we can move on to the next reagent bottle. So we have mixture 2 here. To all of the reagent bottles, we will be adding only 20 milliliters of 1-butanol. Again, we have to measure 20 milliliters of 1-butanol. We have measured 20 milliliters exactly here. Now we will be transferring it to this reagent bottle. After transferring the 20 milliliters to reagent bottle 2, which is labeled mixture 2, we can keep it aside and we can move on to reagent bottle 3 as well, and we can add 20 milliliters of butanol to the reagent bottle 3 also. We have now measured 20 milliliters of butanol here. After that, we can now transfer it to the third reagent bottle. We can place a stopper, and then we can move on to the fourth reagent bottle. We need a few more drops of butanol. Again, after measuring 20 milliliters accurately, we can transfer it into our fourth reagent bottle. Then we will place a stopper here. And finally, we move on to our fifth reagent bottle, and we will measure 20 milliliters to the fifth reagent bottle as well. We can add a few more drops. Now students, we have measured the last portion of butanol, and we have transferred it to the fifth reagent bottle as well. So to all of the 5 different reagent bottles we have now accurately measured 20 milliliters of butan-1-ol or 1-butanol. After measuring 20 milliliters of butanol into each of these reagent bottles, it is now time for us to add the ethanoic acid into each of these reagent bottles. So to add ethanoic acid very accurately, we have here a burette that is filled all the way up to the 0 calibration mark using 2 moles per decimeter cube concentrated ethanoic acid solution. So what you have in here is 2 moles per decimeter cube concentrated ethanoic acid solution, and we have filled it all the way up to the 0 line. Now students, after measuring 20 milliliters of butan-1-ol or 1-butanol into each of these reagent bottles, it is now time for us to measure different volumes of 2 moles per decimeter cube concentrated ethanoic acid into each of these reagent bottles. And we have a solution of ethanoic acid that we prepared earlier. So the concentration of this ethanoic acid is 2 moles per decimeter cube, and we have now filled this burette with this 2 moles per decimeter cube concentrated ethanoic acid. We have filled the burette all the way up to the 0 line. Now we are going to use this burette to accurately measure the volume of ethanoic acid that should be present in each of these reagent bottles. So for the first reagent bottle, we need to add 10 cubic centimeters of ethanoic acid, then to the second one 15, third one 20, fourth 25, and last one, or the fifth reagent bottle, we need to add 30 cubic centimeters of ethanoic acid. So we'll take the first reagent bottle and we will add 10 cubic centimeters of ethanoic acid. So since the burette reading right now is 0, we need to add a volume of 10 milliliters. That means the final reading should be 10 cubic centimeters. So we are going to add ethanoic acid exactly 10 cubic centimeters with the use of this burette. So slowly we will add the ethanoic acid like that, and as the meniscus aligns with the 10 cubic centimeter line, I will stop adding ethanoic acid at that point. Right now we are at that point. Yes, exactly 10 cubic centimeters of ethanoic acid is added. Bottom of the meniscus has perfectly aligned with the 10 cubic centimeter line, indicating we have added exactly 10 cubic centimeters of ethanoic acid to the very first reagent bottle. I will place it here, and then I'm going to move on to the second reagent bottle. To the second reagent bottle, I need to add 15 cubic centimeters of ethanoic acid solution. So the current reading of the burette is 10 cubic centimeters. So if I want to add 15 cubic centimeters, I need to empty the burette all the way up to 25 cubic centimeters, so that I add exactly 15 milliliters onto this reagent bottle. So let's add exactly 15 milliliters of ethanoic acid into the second reagent bottle. So I will stop when the meniscus comes all the way down to the 25 milliliter line. It is getting close to the 25 milliliter line. Now it is exactly on the 25 milliliter line, indicating that we have added exactly 15 milliliters of ethanoic acid into the second reagent bottle. So to the first reagent bottle we added 10 milliliters, and then to the second one we added 15 milliliters of ethanoic acid. So after adding the ethanoic acid, we can stopper the reagent bottle and place it over here. So reagent bottle 1 and 2 is now added with ethanoic acid. We can move on to reagent bottle 3. To the reagent bottle 3, we need to add 20 milliliters. Now the burette reading as it stands is 25 milliliters. So if you add 20 milliliters, the burette reading should go to 45 milliliters. So I will be adding ethanoic acid to this reagent bottle until the burette reading comes all the way down to 45 milliliters. Now we add 43 milliliters, 44, and we are all the way at 45 milliliters now. So students, we have added exactly 20 milliliters of ethanoic acid onto our third reagent bottle here. So then to the fourth reagent bottle and the fifth reagent bottle, we need to add 25 and 30 milliliters. As you can see very clearly here, we do not have enough of a volume left in the burette to do that. So we'll come back after we have filled the burette all the way to the zero line. Now since we have filled the burette again all the way up to the zero line, we can now proceed to add 25 milliliters of ethanoic acid onto this reagent bottle. So since we have filled it all the way up to the zero line, we have to add exactly 25 milliliters by bringing down the meniscus all the way down to the 25 milliliter line here. So let's proceed to do that. We have added exactly 25 milliliters of ethanoic acid to our fourth reagent bottle as well. So to our fifth reagent bottle, we have to add 30 milliliters. We do not have 30 milliliters remaining here. We will have to refill the burette and then we will come back and fill the remainder of the reagent bottle. Now students, we are going to add 30 milliliters to this region bottle 5. Before that, we have filled the burette again all the way up to the zero line. So we can directly add 30 milliliters to this reagent bottle by emptying the burette all the way up to 30 milliliters. So let's add 30 cubic centimeters or 30 milliliters of ethanoic acid to this fifth reagent bottle. We have added exactly 30 cubic centimeters of ethanoic acid. Now we can stop at the bottle and keep it aside. By now, students, we have added the correct amount of ethanoic acid to each of the reagent bottles. To mixture 1, we have added 10 cubic centimeters of ethanoic acid. Then to reagent bottle 2 or mixture 2, 15 cubic centimeters. To mixture 3, 20. Mixture 4, 25 cubic centimeters of ethanoic acid. And finally, to mixture 5, we have added 30 cubic centimeters of aqueous ethanoic acid solution. Now, all that is left for us to do is to add water to each of these mixtures. So to do that, we have distilled water here along with a measuring cylinder we'll be using to add the right volume of distilled water to each of these mixtures. To mixture number 1, we need to add, if you take all of these back, to mixture number 1, we need to add exactly 25 milliliters of distilled water. So we have a measuring cylinder that can measure all the way up to 25 milliliters. So we are going to measure 25 milliliters of distilled water and add it to mixture 1. So let's measure 25 milliliters of distilled water. We have measured exactly 25 milliliters of distilled water here. Now we will be adding this volume of distilled water into our mixture 1. You would notice as you add water that there are 2 layers formed here very clearly. Earlier on, when there was only a small aqueous layer, when I added just 10 milliliters of aqueous ethanoic acid solution, these 2 layers were not very clearly visible. But now that we have a large water layer and a 1-butanol layer here, you can very clearly see that there are 2 layers are present in this mixture. What you see above is the 1-butanol layer, and what you see below is the water layer. The heavier layer, or the layer with more density, will be found at the bottom, and layer with the lower density will be found at the top. So we have 1-butanol layer on top and water layer on the bottom. We will keep it aside for the time being. Then we can move on to mixture 2. To mixture 2, we will be adding 20 milliliters of water. So we need to measure exactly 20 milliliters of water. Now we have measured exactly 20 milliliters of water. Now we will add these 20 milliliters of water into our mixture, into our mixture 2, and then we will stopper the reagent bottle and we will place it aside. And to the third reagent bottle, we need to add 15 milliliters of water. So let's measure 15 milliliters of water using this measuring cylinder. We have taken 15 milliliters of water into the measuring cylinder. So after measuring 15 milliliters of distilled water, we can transfer that volume of water into our reagent bottle here, labeled mixture 3. After transferring the water into mixture 3, we can stopper the reagent bottle, place it aside, and we'll be moving on to mixture 4. And to mixture 4, we need to add 10 milliliters of distilled water. So let's measure 10 milliliters of distilled water. We have measured exactly 10 milliliters of distilled water. After measuring the 10 milliliters of distilled water, we can transfer that into our reagent bottle 4. Now our reagent bottle 4 is ready. We can then stopper the reagent bottle 4, and we can now move on to the final reagent bottle labeled mixture 5, and to it we are going to add 5 milliliters of distilled water. So let's measure 5 milliliters of distilled water. Now we have measured 5 milliliters of distilled water, and we can transfer that 5 milliliters into our reagent bottle like so, and we can stopper it and keep it aside. Now students, at this point we have prepared our 5 mixtures. We have an equal volume of aqueous layer in each of these mixtures and equal volume of 1 butanol layer in each of these mixtures. We have 20 milliliter layer of 1 butanol and 35 milliliter layer of aqueous solution. However, the number of moles of ethanoic acid in each of these mixtures is going to be different because we added different volumes of the same ethanoic acid solution into each of these reagent bottles. So therefore, the number of moles of ethanoic acid in each of these reagent bottles is going to vary. Then, after making that observation, before we move on to the titrations, what we need to do is, you can see that there are 2 layers very clearly. We need to mix these 2 layers at least for 5 minutes. So we need to shake it really well, and we need to make sure that each reagent bottle is shaken for at least 5 minutes. You can see once you shake it, the 2 immiscible layers are mixed well, but as you allow it to settle, the 2 layers will again separate. We'll observe that again. You can see initially, after mixing it for a while, it appears to be an emulsion. However, in a short period of time, you can see that they again will separate out. We will mix these 2 layers like so for 5 minutes to ensure that the ethanoic acid in the aqueous medium is going to come into contact or going to spread well in the 1 butanol layer as well. And if you leave it for another period of time after shaking it really well, they will obtain a dynamic equilibrium where ethanoic acid will move from the aqueous layer to the 1 butanol layer at the same rate at which ethanoic acid in the butanol layer moves to the aqueous layer. So at that point we can say a dynamic equilibrium has been obtained. And we will allow the system to obtain that dynamic equilibrium. Afterwards, we will withdraw an aliquot of the upper layer and the lower layer separately, and then we will carry out a titration to calculate the exact number of moles of ethanoic acid that is present in each layer. Using that information, you can proceed to calculate the concentration of ethanoic acid in each layer. It will allow us to calculate the distribution coefficient of ethanoic acid between water and 1-butanol. So students, we will come back after we have mixed each of these mixtures for 5 minutes, and after we have allowed them to settle for a considerable period of time, we will come back for the next part of this experiment. Now students, we have mixed each of these mixtures for 5 minutes, and we have allowed them to settle so that the two layers have very clearly separated again. You can see, if you take the mixture 1, if you observe here, there are two layers that are separated. So now we need to find out the concentration of ethanoic acid in each layer. In order to do that, we need to withdraw 10 milliliters of the upper layer, which is our 1-butanol layer, and a 10 milliliter volume of the aqueous layer that is found at the bottom as well. So from the two layers, we need to withdraw 10 milliliters each. It is going to be somewhat difficult to withdraw the 10 milliliters while it is present in this reagent bottle. So we will use a separatory funnel as well. So we are going to first introduce this mixture into the separatory funnel, and then we will be using the separatory funnel to separate out the two layers, and then we can obtain our 10 milliliter samples of water and butanol layer into two separate beakers. First, we will transfer this mixture into our separatory funnel that we have over here. We'll make sure that the stopcock is tightly closed, and then we will transfer this mixture over to our separatory funnel. After transferring all of the mixture, you can see now again the mixture got mixed a little bit as we transferred the mixture to the separatory funnel. Now students, we have allowed the layers to separate again. So at this point, we have two beakers that are labeled aqueous layer and butan 1-ol layer. So to this beaker that is labeled aqueous layer, we will be withdrawing the aqueous layer now. So we can open this stopcock and allow the aqueous layer to get collected in the beaker. You can see the interface is coming down. So here the butan 1-ol water interface is here. So as soon as the interface gets to the stopcock, we will tightly close the stopcock and we will separate out our aqueous layer. So what we have here is our aqueous layer out of the two layers, and then we can use an additional beaker if you want to remove the small amount of water that we might have not been able to properly separate out. Then after we are sure that all of the water is removed, we can take our beaker labeled butan 1-ol and transfer our 1-butanol layer or butan 1-ol layer into this second beaker we have over here. Now students, after separating out the butane 1-ol layer and the aqueous layer, we can set aside our separatory funnel and we can now move on to withdrawing 10 cubic centimeters of our butane 1-ol layer. We have a conical flask labeled butane 1-ol layer. To that, we will transfer 10 cubic centimeters of butane 1-ol with the use of a volumetric pipette. This is a graduated pipette, so we will use a graduated pipette and we will transfer 10 milliliters of this butane 1-ol layer into this titration flask. We will use a pipette filler to withdraw 10 milliliters. We will measure exactly 10 milliliters. So we have measured 10 cubic centimeters here. We are going to transfer that into this titration flask here. As you can remember, when you're transferring it, make sure the tip of the pipette is touching the internal wall of the titration flask so that we can easily transfer all of the butane 1-ol layer into the titration flask without any issue. Now we have transferred the butane 1-ol layer into our titration flask here. It is now time for us to add 25 milliliters of distilled water. To measure 25 milliliters of distilled water, we will use a measuring cylinder. We have measured 25 cubic centimeters of distilled water. Now we will transfer this into our titration flask. After transferring the water, you can mix the two immiscible layers. As you remember, butane 1-ol and water is not miscible, so to make sure that some of the ethanoic acid that is in the butane layer comes into the aqueous medium right now, you can mix it a little, and then after that you can proceed to add 3 drops of phenolphthalein. Add 3 drops of phenolphthalein. After adding the phenolphthalein, after mixing it well, we can now proceed to titrating this mixture. So in this burette we have filled this burette with 0.5 moles per decimeters cube concentrated sodium hydroxide solution. We have prepared this solution earlier, and then we have filled the burette all the way to the zero line. So now this burette is ready. We can use this burette filled with 0.5 moles per decimeters cube concentrated sodium hydroxide to carry out this titration. So we will place this titration flask underneath the burette like so, and by now, students, you have to be aware of how to handle a burette and how to carry out titration. So using the correct techniques, we will be carrying out this titration. We will slowly add sodium hydroxide to our titration flask little by little, and at one point you will observe a permanent pink color in the medium. At that point we will record the burette reading because that is going to be our end point. We will gradually add sodium hydroxide like so. When you are adding sodium hydroxide, let's talk about what happens in this mixture. Now, when the butan 1-ol layer was transferred here, and then when 25 milliliters of water was added, again we created 2 layers. However, as I titrate this mixture, the ethanoic acid in the aqueous layer will get used up. As ethanoic acid in aqueous layer gets used up, since there is an equilibrium between the ethanoic acid dissolved in butan 1-ol layer and aqueous layer, as aqueous layer ethanoic acid concentration goes down, ethanoic acid from butanol layer will come into the aqueous medium. So we will continue to keep on titrating this aqueous layer by adding more and more sodium hydroxide, and as more and more ethanoic acid gets used up from the aqueous layer, when the aqueous layer ethanoic acid concentration goes down, ethanoic acid from the butanol layer will come into the aqueous layer. So this way we can extract the ethanoic acid that was in butanol layer into the aqueous medium, and all of the ethanoic acid will be completely reacted when phenolphthalein indicates a color change. So at the point at which phenolphthalein gives us a color change, that is going to be the point where all of the ethanoic acid, not only in aqueous layer but also in butan 1-ol layer, has reacted with sodium hydroxide. So we will make sure that all of the ethanoic acid in butanol layer is reacted, and that will be the point at which we will see a color change in phenolphthalein. And now we will proceed to titrate. You can see now we are somewhat close to the end point, because we can very clearly see when we add a drop of sodium hydroxide, there is a slight pink color that we can see, but that color disappears after a while. So we'll very carefully now add sodium hydroxide drop by drop. Now students, we are very close to the end point. We can see when we add a drop of sodium hydroxide, the pink color is more and more persistent in the medium, indicating we are close to the end point. I think we have obtained our end point here. You can see with just one drop, the entire mixture turned pink. This indicates that all of the ethanoic acid is now completely reacted, and the excess sodium hydroxide in the medium turns the phenolphthalein into a pink color, because the medium is now basic. So the butyrate reading at this point, we can read the butyrate reading by bringing this down to eye level. So the butyrate reading at this point is 8.7. Butyrate reading is 8.7. So we have to note down the butyrate reading, and then we can move on to titrating the aqueous medium. Now students, we observed that to titrate the butan 1-ol layer that we took into this titration flask, 8.7 milliliters of 0.5 moles per decimeter cube concentrated sodium hydroxide was spent. So now let's keep that aside, and we can move on to our aqueous layer. So to withdraw the aqueous layer, we will be using a different pipette. So we will remove the pipette filler from that previous pipette, and then we can fix the pipette filler to this new pipette we have here, and then we will withdraw 10 milliliters of the aqueous layer into this pipette. After withdrawing 10 milliliters of water into this pipette. We can now transfer that into our titration flask. After transferring 10 milliliters of the aqueous layer, we can now move on to measuring 25 milliliters of distilled water. We can use a measuring cylinder and then add 25 milliliters of distilled water to this measuring cylinder. Right, we have measured 25 milliliters of distilled water into this measuring cylinder. Now, we are going to transfer this into our titration flask. And then we will add 3 drops of phenolphthalein. Then we can mix the solution well. Here we only have an aqueous layer. We took the aqueous layer from the mixture 1 and then we added 25 milliliters of additional water to this to make the entire volume 35 milliliters, and then we added it with the phenolphthalein indicator. Now students, we are going to titrate this solution using 0.5 moles per decimeter cube concentrated sodium hydroxide solution. When it comes to this titration, we are starting this titration at 8.7 burette reading. If you can remember, in the previous titration, we added 8.7 milliliters of sodium hydroxide to titrate the organic layer or butane 1-ol layer. So over here we have the aqueous layer. So when we are starting the titration, the burette reading is, or initial burette reading is 8.7. And after the endpoint is observed, we have to get the difference between the initial reading and the final reading to obtain the volume of sodium hydroxide that was added to the titration flask here. So let's proceed to titrate this aqueous layer. Now students, you can see as sodium hydroxide is added to the titration flask, initially you can see a small pink coloration appears, but it quickly goes away as we mix the solution. This indicates that the concentration of ethanoic acid in the medium is still high, because if the concentration was very low, the phenolphthalein color will be a bit more persistent. So we can identify whether we are closing in on the endpoint based on how fast the pink color disappears from the solution in the titration flask. So we are still not very close to the endpoint. We can now proceed to add sodium hydroxide drop by drop like so. We can see now the pink color is a bit more persistent in this aqueous medium, indicating we might be close to the endpoint. We can now proceed to add sodium hydroxide drop by drop. You can see as we mix the medium, the pink color is still there, indicating the concentration of ethanoic acid is very low. You can see the pink color is still very persistent. This indicates we might be just a single drop away from the endpoint. So we'll very carefully add just a single drop of sodium hydroxide to obtain our endpoint. So we have added just a single drop. Let's see if this color remains. Yes, students, you can very clearly see now the color is remaining. It is not going away, indicates that we have obtained our endpoint successfully. Now students, the burette reading is 15.8. The Buret reading is 15.8. So we have obtained the Buret reading, or the volume of sodium hydroxide that was spent on the aqueous medium. So when it comes to this titration, the initial Buret reading was 8.7, and then the final Buret reading is 15.8. So 15.8 minus 8.7 will give us our volume of sodium hydroxide that was spent on this titration. So 15.8 minus 8.7 is 7.1. 7.1 milliliters, or 7.1 cubic centimeters of sodium hydroxide was spent on titrating the aqueous layer. Now students, we have to note down the volumes of sodium hydroxide that was spent for titrating the butane 1-ol layer and the aqueous layer. After that, we need to move on to the second mixture. Before we move on to the second mixture, keep in mind you need to wash and dry the separatory funnel that you used, as well as you need to fill this burette all the way to the zero line again. So let us do those things and come back and titrate the organic layer, or the 1-butanol layer, and the water layer of the second mixture. Now students, we move on to the second mixture, mixture 2. So like we did in the previous step, we are going to use a separatory funnel to separate the two layers. So before we pour the mixture into the separatory funnel, we have to make sure the stopcock is tightly closed. After that, we can place our beaker labeled aqueous layer, like so, and then we can proceed to transfer the second mixture onto our separatory funnel. As we transferred our second mixture to the separatory funnel, we saw that the two layers were mixing up again, so we will allow it to settle for a while. After allowing it to settle for a while, we will separate the two layers. Now students, we have allowed the two layers to settle for a while, so we can now open the stopcock here and remove the bottom layer, which is the water layer or the aqueous layer of the mixture, into this beaker. As the interface reaches the stopcock, we will close the stopcock tightly, and by then we would have removed the aqueous layer separately. So we have separately taken off our aqueous layer, and then we can take another small beaker, because there might be a small amount of water that is still present near the stopcock area. We can remove that by allowing few drops to run down, like so, and then after that we can proceed to separating the organic layer, which is butane 1-ol layer, into a separate beaker. This beaker is also labeled butane 1-ol, so that we can identify this layer easily. If you don't label clear solutions in two separate beakers, if you place them side by side, you will not be able to identify which one is the aqueous layer and which one is the butane 1-ol layer without smelling them. And we would not necessarily like to smell different compounds in the lab to identify them. Instead, labeling is a better option. So therefore students, when you are carrying out this type of experiments in the lab, please make sure to label the beakers, so then it will be easier for you to identify what layer is in which beaker. We will place the separatory funnel aside for the time being, and we can use the pipette we used to withdraw the butane 1-ol layer. Again, this pipette, we used it earlier to withdraw butane 1-ol layer. Now it is clean and dried. We will use the same pipette to withdraw exactly 10 milliliters of butane 1-ol layer, and then we will transfer it to this titration flask. So let's transfer 10 milliliters. Of the organic layer into our titration flask. You can see we have taken 10 milliliters, and now we are transferring this 10 milliliters into the titration flask. After all of the butane 1-ol has been transferred into the titration flask, we can keep the pipette aside, and we can move on to adding 25 milliliters of distilled water. So let's measure 25 milliliters of distilled water into this measuring cylinder. Now students, we have added 25 milliliters of distilled water to this measuring cylinder. We can transfer it into our titration flask, and then we will proceed to add 3 drops of phenolphthalein. After adding 3 drops of phenolphthalein, we can mix this immiscible mixture, and then we can proceed to titrate it. Now, after adding this with phenolphthalein and mixing it really well, we can now proceed to titrate this mixture using 0.5 moles per decimeter cube concentrated sodium hydroxide solution. We have taken that solution and we have filled this burette with 0.5 moles per decimeter cube sodium hydroxide solution all the way up to the 0 line. Now, we can place our titration flask underneath our burette here, and we will start our titration. We can start to add sodium hydroxide drop by drop, and then we can stir or mix the mixture really well while we add sodium hydroxide. We can see there are no traces of pink here. That is because there is a high concentration of ethanoic acid still in the mixture. So therefore, we do not observe a very clear pink coloration here yet. But as we add more and more sodium hydroxide, we are starting to observe a slight pink hue when sodium hydroxide is introduced into the mixture here. You can see there's a slight pink hue, but when you mix it, it will disappear. Over here also, you can see when sodium hydroxide, few drops of it is added here, you can see there's a slight pink hue, but as you mix it, it will disappear. This indicates we are still not at the end point. At the end point, we will notice that the pink color will not disappear. We will slowly add sodium hydroxide drop by drop now. Now students, we can see that there is a slight permanent pink coloration in this mixture, indicating we have obtained an endpoint. We will start mixing it further to observe if this pink color disappears. If it disappears, we have not obtained the endpoint correctly. That means we have to add one additional drop. So as you mix it, you can see the pink coloration completely disappears. This indicates we are not at the end point yet. Maybe one additional drop is required. You can see there is no pink coloration now, indicating that we are still not at the end point. We can add one more drop and you will observe that the pink color then will not disappear after that. So let's observe what happens when one additional drop is added. There is a slight pink color there. You can add another drop. At this point, students, you can see that there is a permanent pink color. This pink color indicates that we have obtained our endpoint. But again, we will observe if the pink color disappears. If it does disappear, we can add another drop of sodium hydroxide until a permanent pink color is observed. Now students, you can see after mixing it and allowing it to settle for a while as well, there is still a pink hue or very clear pink coloration in the mixture, indicating that we have obtained our endpoint. So at this point, students, we have obtained our endpoint. We can very clearly see that this mixture is pink in color. So the butyl reading at the endpoint is 13.4. The butyl reading at the endpoint is 13.4. So we have added 13.4 milliliters of sodium hydroxide to react with 10 milliliter liquid of our butane 1-ol layer. So we withdrew 10 milliliters of the butane 1-ol layer from the mixture 2, and to react with it, we have spent 13.4 cubic centimeters of our sodium hydroxide solution. Now, let's move on to the second titration, where we will take our aqueous layer and titrate 10 milliliter liquid of the aqueous layer. Now we have our aqueous layer here, and we will take a titration flask here. And students, we have a pipette that is used only for removing the aqueous layer from the mixture. So we have this new pipette that we will be using for withdrawing 10 milliliters of aqueous layer into our pipette here. You have to withdraw exactly 10 milliliters of the aqueous layer, and then we can transfer it directly into our titration flask. Now we have transferred our aqueous layer into the titration flask. Then, like we did in the previous steps, we have to measure 25 milliliters of distilled water. Now we have measured 25 milliliters of distilled water. We will transfer this into the titration flask. And then, students, we are going to add, like we did in the previous steps, 3 drops of phenolphthalein into the titration flask. After that, we will mix the solution well and we will place our titration flask under the burette. So the previous reading was 13.4, so we can still see the 13.4 initial burette reading over here, and then from here we will start to add sodium hydroxide to this titration flask. So therefore, students, you note down the initial reading to be 13.4, and then we will have the final reading. The difference between the two readings will be the volume of sodium hydroxide that is added to this titration flask. So we will slowly add a few drops of sodium hydroxide little by little into the titration flask. We can see initially when sodium hydroxide enters the medium, it will quickly disappear when mixed. But as I mentioned earlier, close to the end point, we will see that this pink color will not easily disappear. We will drop by drop add sodium hydroxide to our titration flask. And you can see as soon as the sodium hydroxide enters the medium, there will be a pink coloration, but it will disappear after we mix it. We have not yet obtained the end point, but you can see the pink color that you observe is a bit stronger compared to the previous times, indicating we are nearing the end point. So you can see now with just one drop, there was a very clear and very strong pink color that we obtained, and at that point the reading is 24.3. The reading is 24.3. You can see the pink color does not disappear upon mixing, indicates that we have obtained the end point. So over here you can very clearly see very slight pink color that indicates majority of the last drop of sodium hydroxide added reacted with the acid remaining, and only a small amount of sodium hydroxide was there in the medium to make the medium alkaline. That is why there's only a very slight hue of pink. But as it stands, if the pink color disappears, that indicates again the medium is not alkaline. So we will allow it to stand for a while and observe whether the medium is becoming colorless, and if it does become colorless, we will have to add another drop. Now students, as we wait, we can see the color has completely disappeared, which means we have to add another drop of sodium hydroxide. And then we mix it. You can very clearly see a strong pink color, because at this point we have enough and more sodium hydroxide to react with whatever the remaining amount of ethanoic acid. A very small quantity of ethanoic acid might have stayed on the mixture. Now all of them have completely reacted, and the additional drop that was added has now completely turned this solution into a pink color. Now students, let's take a look at the burette reading after we obtained the end point. At the end point, the final reading is 24.4. The final reading is 24.4. After obtaining the final burette reading, we can calculate the volume of sodium hydroxide that was spent on titrating this aqueous layer that we have obtained from the mixture 2. So to titrate 10 cubic centimeter aliquot of the aqueous layer from mixture 2, we have spent a total of 11 cubic centimeters. So the amount of sodium hydroxide spent to titrate our aqueous layer was exactly 11 cubic centimeters, and we have spent 13.4 cubic centimeters to titrate our organic layer. Now students, we move on to the third mixture. And as we did in the previous instances, we'll be transferring this third mixture onto our separatory funnel here, making sure the stopcock is very tightly closed. We can now proceed to transfer our third mixture into the separatory funnel. So students, after transferring the mixture in reagent bottle into our separatory funnel, there may be some mixing taking place which will disturb the dynamic equilibrium. So therefore, we will allow these two layers to settle for a while so that it may obtain the equilibrium once more. So we will allow it to sit here for a while, and then after a while we will come back and we will separate the two layers. So the bottom layer, which is the aqueous layer, will be taken into a beaker labeled the aqueous layer like we did before, and as you know, we will take the second layer into a beaker labeled butane 1-O layer, which is going to be our organic layer. So we will allow it to settle for a while, and we'll come back and withdraw the two layers into two separate beakers. Now students, we have allowed the two layers to separate when it comes to our mixture 3. Now we can open the stopcock and take the aqueous layer into this beaker which is labeled. When you open the stopcock, if the lid of the separatory funnel is still there, then the bottom layer will not come out easily. So make sure to remove the lid. Now we can see the interface is here. As the interface comes to the stopcock, we will close this stopcock tightly. We have now taken only our aqueous layer into this beaker which is labeled. We can then take another beaker because there is still a small amount of aqueous medium here, so we will remove that from there, and now we can proceed to take just the butane 1-O layer into a separate beaker. Now students, we have separated the two layers into two different beakers. We can leave the separatory funnel aside, and we can take our burette here and we can proceed with our titration. In order to carry out our titration, we will first take a conical flask and we will transfer 10 cubic centimeters of the butane 1-O layer, 10 cubic centimeters of the butane 1-O layer onto our titration flask. So as you have seen in the previous steps, we will use a pipette with a pipette filler to withdraw 10 cubic centimeters of our butane 1-O layer. After withdrawing exactly 10 cubic centimeters of butane 1-O layer, we can move to add this onto our titration flask. Now we have transferred the butane 1-O, 10 cubic centimeters of butane 1-O to our titration flask. Now it is time for us to measure 25 milliliters of distilled water into our measuring cylinder. We have taken exactly 25 cubic centimeters of distilled water to the measuring cylinder, and now we will transfer that into our titration flask. Afterwards, to the same titration flask, we can proceed to add 3 drops of phenolphthalein. We can then mix it really well. Then we can place it under the burette like so. Afterwards, students, we can proceed to the titration. So it is important to notice that we have filled the burette all the way to the 0 line. So, and this burette is filled with sodium hydroxide solution that we used in the previous instances as well, which is 0.5 moles per decimeters cube concentrated sodium hydroxide solution. And now we can proceed to add sodium hydroxide until we observe a color change. We can see now we are close to the end point. You can see there is a slight pink hue you observe as sodium hydroxide enters the medium. We are planning on observing a permanent pink hue, and this will indicate that we have obtained the end point. So at the end point, we will observe a permanent pink color, giving us the end point for this titration. We can see that there is a slight pink hue still in the medium. We will mix it and observe it for a while to observe whether the pink color disappears. If that is the case, we have not yet obtained the end point. Now, students, the pink color in the medium is no longer visible, so therefore we have not yet obtained the end point. We can proceed to add 1 drop and we can mix it to see if we can observe a permanent pink color. Now, students, we can very clearly see that we have obtained our end point. So we have a permanent pink color at this point, which doesn't seem to be going away. So at this point, students, we need to take the burette reading. Burette reading is 18.0. Burette reading is 18.0, indicating that we have spent exactly 18 milliliters of our sodium hydroxide solution. So after obtaining that burette reading, we can now proceed to withdrawing 10 milliliters of the aqueous layer, and we will carry out the titration as we did in the previous instances as well. So we'll first take 10 milliliters of the aqueous layer, and then we'll transfer it to our titration flask here, and we will add 25 milliliters of distilled water to this along with some phenolphthalein, and then we'll proceed to our titration. Now we will connect the pipette that we usually use to withdraw the aqueous layer into a pipette filler. We have connected that pipette into the pipette filler, and we have our aqueous layer over here. Out of the 2 layers in the mixture, the aqueous layer was taken to this beaker. So now we are going to withdraw 10 cubic centimeters of the aqueous layer. We have measured 10 cubic centimeters of the aqueous layer here, and we will transfer it to our titration flask over here. And afterwards, students, you can proceed to add 25 cubic centimeters of distilled water. Afterwards, we are going to add this 25 cubic centimeters of distilled water into our titration flask. Then we will add 3 drops of phenolphthalein. And we will mix this solution and we will proceed to our titration. The initial reading is 18 cubic centimeters. We added 18 cubic centimeters of sodium hydroxide to titrate our organic layer. So now we are titrating our aqueous layer. So over here, we are starting the titration with a butyrate reading of 18 cubic centimeters. So now let's add sodium hydroxide little by little. We will slowly start to add sodium hydroxide to this aqueous layer we have here. You can see the pink color is slightly more persistent at this point, indicating that the ethanoic acid concentration in the mixture is now starting to go down, and we might have a low concentration of ethanoic acid in the mixture now. So we can start to add sodium hydroxide more carefully. We have almost obtained the end point. It's still not there. We have added a few more drops of sodium hydroxide. We'll add just one more, and let's observe whether the color is going to be persistent this time around. There is a pink color, but the pink color is not very persistent, indicating we have not yet obtained the endpoint. The pink color has completely disappeared now. We can add another drop of sodium hydroxide. Again, we can see a good pink color. However, we'll have to observe whether the pink color is persistent or not. Now students, upon mixing and allowing it to stand for a while, you can see the pink color has disappeared. At this point, we can add. Now we have added a drop of sodium hydroxide. You can see that there is a very clear pink color here. Let's mix the solution and see if the pink color disappears at this point. The pink color does not disappear at this point, indicating that we have obtained our endpoint. The final reading is 32.6. The final reading is 32.6 cubic centimeters. The initial reading was 18 cubic centimeters. The amount of sodium hydroxide that we added to the titration flask here is going to be the difference between the initial and the final butyrate readings. So therefore, the volume that we added here is 14.6 cubic centimeters. Initial reading was 18, final reading is 32.6. So therefore, the volume of sodium hydroxide we added into this titration flask is going to be 14.6 cubic centimeters. Now students, we have to note down these volumes and then we can move on to the fourth mixture. Now students, we move on to mixture 4. We have our mixture 4 here. Like we did in the previous instances, we will make sure that the separatory funnel stopcock is tightly closed, and we will place the beaker labeled aqueous layer underneath it, because we will be extracting the aqueous layer first, and then we will carefully transfer this fourth mixture into our separatory funnel. After transferring the fourth mixture into the separatory funnel, we'll allow it to settle for a while for it to obtain the equilibrium again. After that, we will start to extract the aqueous layer into this beaker and the butane 1-ol layer into a separate beaker. Now students, we have allowed these two layers to separate for a while. Now we can separate our aqueous layer of this mixture into the beaker we have over here. And as the interface between the butane 1-ol and aqueous layer comes close to the stopcock, we have tightly closed the stopcock and we only have the aqueous layer remaining in this beaker. We have taken the aqueous layer into a beaker labeled aqueous layer, and since we have small amount of water still remaining around the stopcock area, we can open the stopcock and take that small amount of water out so that we can be sure when we place the next beaker we are only taking butane 1-ol layer into that beaker. Now we will withdraw the butane 1-ol into this beaker. So we have taken the butane 1-ol layer into this second beaker we have over here, and it is now time for us to keep the separatory funnel aside. After separating the two layers, now we have to withdraw 10 milliliters of butane 1-ol layer into a titration flask. So we have here a titration flask which is labeled butane 1-ol, and we will be using separate pipettes to withdraw both the aqueous layer and the butane 1-ol layer separately. So we have a graduated pipette here which we'll be using for withdrawing the butane 1-ol layer or the organic layer. We have measured exactly 10 cubic centimeters of our organic layer, and we will be transferring it into this titration flask like so. After transferring the butane 1-ol layer into the titration flask, it is now time for us to measure 25 milliliters of water like we did in the previous instances. I measured 25 milliliters of water, and we will transfer that into this titration flask. Afterwards, we'll be adding 3 drops of phenolphthalein indicator. Then we can mix all the contents in this titration flask really well, and then we can proceed to titrating the contents in the titration flask. Keep in mind students, we have filled this burette all the way to the 0 line using our sodium hydroxide solution which we used in the previous occasions as well. Now we will slowly add sodium hydroxide here. By now, students, we have added 18 cubic centimeters of sodium hydroxide, still no color. We can proceed to add a little bit more. We can see now there's a slight pink hue appearing and then disappearing upon shaking. When we swirl the contents in the titration flask, we can see the pink color disappears. At this point, we can be certain that we are somewhat close to the end point, because it takes a while for the pink color to disappear at this point. You can see we have a slightly more persistent pink color, indicating we are somewhat close to the end point. We'll add another drop of sodium hydroxide. Still no permanent color change. As you can see, students, at this point we can observe a pink color in the mixture. We will allow it to stay there for a while. We'll mix it and see if the pink color changes. If the pink color remains, if it does not change to colorless, that indicates we have obtained our endpoint. Since the pink color was disappearing, when another drop of sodium hydroxide was added, we can see a more persistent pink color here. This indicates that we have obtained our endpoint. And the burette reading at the endpoint is 22.6. Burette reading at the endpoint is 22.6. Now, students, we can see that there is a very pale pink color observed here in this mixture. This indicates that the medium is now alkaline. Now, this is a very pale pink color because majority of the sodium hydroxide contained in the last drop that we added was reacted with the ethanoic acid that was present in the medium, leaving behind only a few molecules of sodium hydroxide to make the medium alkaline. So the medium is not very alkaline to give off a very strong pink color. That's why we see a very pale pink color, because the medium is not very alkaline, indicating that we have obtained a good endpoint. At this point, we have all the ethanoic acid completely removed, and the remaining very small number of sodium hydroxide has produced this pink color. So at this point, we should note down the burette reading 22.6. The burette reading is 22.6. Now let's move on to withdrawing 10 milliliters of the aqueous layer and carrying out the same titration. So let's remove this from the setup, and we'll now move on to withdrawing 10 milliliters of the aqueous layer. So to remove 10 cubic centimeters of our aqueous solution, we will be using a separate pipette, and we will withdraw 10 cubic centimeters of our aqueous layer into this pipette, and afterwards we will be transferring it into our titration flask that we have over here. We have to first measure the 10 milliliter volume of our aqueous layer very accurately, and then we can transfer it into our titration flask like so. And after transferring it into our titration flask, we can proceed to add 25 milliliters of water After measuring 25 milliliters of water, we can now transfer it into our titration flask. After that, we can add a few drops, actually 3 drops of phenolphthalein into our titration flask, and then we can mix the contents in the titration flask here. Then we can proceed to our titration with sodium hydroxide. Now students, when you are titrating with sodium hydroxide, remember in the initial titration we did with the fourth mixture, we spent 22.6 cubic centimeters of sodium hydroxide. Now that will be our initial reading. Starting with that initial reading, we will start to add sodium hydroxide into our titration flask that we have here. We will gradually start to add sodium hydroxide, and when we observe a pink color being somewhat persistent in the titration flask, at that point we will slowly add sodium hydroxide drop by drop into the titration flask until a permanent pink color is observed. We can see now the pink color is somewhat more persistent. We can now start to add sodium hydroxide few drops at a time. Now, since the last drop that we added had a more of a persistent pink color produced in the mixture, I have a feeling with just one additional drop, this entire reaction mixture would turn pink. So I added just one additional drop. Even that pink color disappeared, so we can add one more drop of sodium hydroxide very carefully. At that point also, students, we can see that there's a very slight pink color produced here, but if you keep on mixing it, if it disappears, at that point we will have to start adding another drop, or we'll have to add another drop to obtain our endpoint. You can see that it is now entirely colorless, this solution. So therefore we will have to add another drop of sodium hydroxide into the medium, so that the entire medium turns to a more permanent pink color. Since the pink color disappeared once more, we will be adding just a single more drop of sodium hydroxide into the medium. Now you can see a very persistent pink color is produced here. So we can now observe a more persistent pink color. Take a look at the Bury reading at this point. The Bury reading at this point is 41, exactly at 41. So the initial reading was 22.6 and the final reading is at 41. So 41 minus 22.6 is 18.4. 18.4. So the volume that we added into our titration flask over here, or volume of sodium hydroxide we added into our aqueous layer to titrate it, was exactly 18.4 cubic centimeters. So we have added 18.4 cubic centimeters of our sodium hydroxide solution to titrate the aqueous layer of mixture 4. After noting down the volume of sodium hydroxide added to the aqueous layer, we can now move on to our fifth mixture. Now students, we are moving on to the fifth and the final mixture. And like we have done in the previous instances, we will take a beaker labeled aqueous layer, place it under our separatory funnel. We'll make sure the stopcock of the separatory funnel is tightly closed, and then we will proceed to add our mixture 5 onto our separatory funnel. Afterwards, students, like we have allowed in the previous 4 instances, we will allow these 2 layers to settle for a while so that they can obtain the equilibrium again. So after we allow them to get separated into 2 layers one more time, we will return to this part of our experiment, and we will extract our aqueous layer to this beaker. So we will allow them to separate for a few moments, and then we will be back to extract the aqueous layer. Now students, we are joining you after we have allowed these 2 layers to settle for a while. Now we are going to be opening this stopcock, and we will collect the bottom aqueous layer into this beaker that we have over here. So now, although I open the stopcock, you might have noticed that the bottom layer is not coming down. That is because the lid is still here. You need to remove the lid for the aqueous layer to come down. You can see the interface slowly coming close to near the stopcock. So interface is slowly coming near the stopcock. So as it reaches the stopcock, we will tightly close the stopcock, making sure that only the aqueous layer is taken into our beaker labeled the aqueous layer. Then we can keep the aqueous layer aside, and as we have done in the previous 4 instances, we can remove small volume of liquid over here, which is going to be a mix of butane 1-ol layer and remaining aqueous layer. So after we remove that, in this area of the separatory funnel, we now only have the butane 1-ol layer. Then we can open our stopcock, and we can take our entire butane 1-ol layer onto the beaker we have here. Afterwards, students, since we would no longer need the separatory funnel, we can keep it aside. Then we can take our butane 1-ol layer along with a titration flask labeled butane 1-ol, and we can transfer 10 cubic centimeters of butane 1-ol into the titration flask with the use of a graduated pipette. We will measure exactly 10 cubic centimeters of butane 1-ol with the use of a graduated pipette. Then we can very carefully transfer it into our titration flask, like so. After transferring our butane 1-ol 10 milliliters of the butane 1-ol layer into our titration flask, we will add 25 milliliters of distilled water into the titration flask. We have measured 25 milliliters of water into a measuring cylinder. Then we will transfer it to our titration flask here. Afterwards, we will add 3 drops of phenolphthalein indicator, and then we'll mix the contents in the titration flask thoroughly, and then we can proceed to titrate this mixture. We have our burette filled all the way up to the 0 line, and we have filled this burette with 0.5 moles per decimeter cube concentrated sodium hydroxide, the same solution we used in the previous 4 instances. So using the same solution, we will now carry out our titration. We will gradually start to add sodium hydroxide into our reaction mixture here. You can see in the initial stages you do not observe a pink color. That is because the sodium hydroxide that is added to this mixture is immediately reacted with the ethanoic acid. This 5th mixture has the highest number of moles of ethanoic acid in the mixture. So therefore you can see when we add sodium hydroxide, there is not going to be a pink color visible in the initial stages. You can now see we are starting to see a pink coloration, meaning ethanoic acid concentration is somewhat lowered at this point. We can start to add sodium hydroxide drop by drop until a permanent pink color appears. So the last drop that was added here produced a pink color that was somewhat persistent. So we will add another few drops to observe whether we can see a more persistent pink color. We can see somewhat of a persistent pink color here. Do you observe a pink color here? Right now, there is not a clear pink coloration here. This indicates that the pink color that was present earlier has now completely disappeared. We can add a few more drops of sodium hydroxide to observe whether we have obtained the endpoint yet. With the addition of the last drop of sodium hydroxide, we can now observe somewhat of a more persistent pink color. You can very clearly see a more persistent pink color present here. So at this point, we can conclude that we have obtained our endpoint, and you can see when you mix it around, the pink color does not disappear, indicating that we have obtained our endpoint. Now students, at this point you have to take the burette reading. Burette reading is 27.1 cubic centimeters. So the burette reading is 27.1 cubic centimeters. Now students, we are moving on to taking the aqueous layer. So we can leave the butane 1-ol layer aside. We have another titration flask, and to that we'll transfer 10 cubic centimeters of the aqueous layer of the mixture. To withdraw 10 milliliters of the aqueous layer we have over here, we will be using another pipette, and using a pipette filler we will withdraw exactly 10 milliliters of this aqueous layer of the mixture 5. After measuring exactly 10 milliliters, we will transfer it into our titration flask. Afterwards, we will take our measuring cylinder and we will measure 25 milliliters of water into our measuring cylinder. Now we have measured exactly 25 milliliters of water into our measuring cylinder. We will now move on to transferring that volume of water into our titration flask. And then, as we have done in all of the previous instances before, we will take our phenolphthalein indicator and we will add 3 drops of the indicator into our titration flask. And then we will mix this solution well, and we can proceed to titrate this solution using the sodium hydroxide that is already present in this burette. So the previous reading of the burette was 27.1 cubic centimeters. Now we'll proceed to take that as our initial reading, and we'll proceed to titrate this solution using the sodium hydroxide that is present in the burette. Since the concentration of ethanoic acid is high in the 5th mixture, we can see we do not observe a pink coloration in the initial addition of sodium hydroxide, but after a while we can observe a bit more persistent pink coloration. So at that point we will slow down the addition of sodium hydroxide and will shift to adding sodium hydroxide drop by drop. We can see a more persistent pink color. We are close to the end point. We can add a few more drops. We have a bit of a more persistent pink color here that has still not completely disappeared, but by now, yes, it has completely disappeared. So that means the next few drops that we add will be our last few drops, and if the pink color that we obtain does not completely disappear, that means we have obtained our endpoint. So I just added a single drop. Let's observe whether the pink color that is present here is completely disappearing. Yes, it completely disappeared, meaning we can add another drop. After adding the last drop, we can see there is a persistent pink color. So we will mix it a little bit to observe whether the pink color disappears. We can see, students, the pink color is not disappearing, indicating that this is our endpoint. We have obtained our endpoint. So At this point, we can observe what the butyrate reading is. It is 49.2. The butyrate reading is 49.2. So we have obtained our final butyrate reading, which is going to be 49.2. We started with 27.1 as the initial reading. Final reading is 49.2. So the volume of sodium hydroxide we added to this titration flask in this titration is 22.1. Initial reading 27.1. Final reading is 49.2. So the difference between the two is 22.1. So we have added 22.1 cubic centimeters of sodium hydroxide into this titration flask. Now students, we have gathered all of the measurements we need to calculate the distribution coefficient of ethanoic acid between water and butane 1-ol. As we learned earlier, distribution coefficient is also known as partition coefficient as well, and it is usually signified by Kd. So after collecting all of this data, it is now time for us to move on out of the lab and into our classroom to discuss how we can calculate the distribution coefficient of ethanoic acid between water and 1-butanol.